Python to process physical oceanographic observations. And today's talk is going to be about Python testing fundamentals. And I think the volume here on the mic is a little bit up, a little bit distorted, so hopefully we get that fixed here in just a second. And there are some downloads for this talk. They're at drunkenpython.org. That's sort of a take on Drunken Master. And so there's a PDF file, pytestfun.pdf. There are these slides here exactly, and that will help you keep up with this presentation if you get behind. So you can go and download those. We set this room up here tutorial style so that you can put your laptop out and connect and maybe follow along with this talk, which I encourage you to do. Next of all, there's a zip file and a TGZ file. It has some compressed code in it that you can download. And so I'm just going to move along there. I hope you see those URLs. I know this slide is going by fairly quickly. There's a lot to cover today. First of all, I want you to know that this talk is about Python testing fundamentals. So if you already know about Python testing, prepare to be bored because we are really going to go through the fundamentals. This is a tutorial here today. It's part of a curriculum called PyCamp. It was put together by the Triangle's Open Python Users Group. The Triangle is an area in North Carolina comprised of Durham, Raleigh, and Chapel Hill, where there are three large research universities, and they have a research triangle between them with lots of institutes and centers and so forth. And Tri-Z-Pug is going to be celebrating its 10th anniversary this year with a conference similar to this one called PyCarolinas. I urge you to go to pycarolinas.org and look about that and see if you want to submit a talk proposal. I think Monday is the talk proposal deadline. And this PyCamp program is an intensive week-long training in the basics of Python that we've been doing for about 7 years. And we've spun off now an intermediate PyCamp that includes an entire day about testing. And so this is a very compressed version of that one day. Yes, sir. Thank you. That was causing a problem. So, is that better? No, it's not better. Not worse. It is different. Okay. Less bumpy, less clipped. Okay. Well, this happens every time I give a talk and I'm recorded. You can go watch many videos of me on the web, and every last one is audio distorted, so it's not going to bother me. It's just the way things work. All right. So maybe that's a little bit better? Okay. All right. Well, it's a PA system, so that's the way it is. Second of all, this talk is going to be taking place on Python 3.2.3. And this is a shift for PyCamp because PyCamp was developed on Python 2, and we're revamping all the materials for Python 3.2.3. If you have a previous version of Python 3 before Python 3.2, be aware that many of the testing tools have changed for Python 3.2 and will operate differently in this talk. If you have Python 3.2 installed, I highly encourage you to download the code, expand it out into a directory. It will be called PyOhio, and then go ahead and make a virtual environment on top of that with Python 3.2.3 or Python 3.2 of any sort of minor revision, and we should be good to go. And if you don't want to do that now, just follow along with the talk. I have all the demonstrations we're going to do are going to be on these slides. And in this talk, we're going to look at assertion, which is the most fundamental concept in Python that's applied to testing. Then we'll talk about the unit test module, and then finally the doc test module. And there's much more to Python testing than just assertions, unit tests, and doc tests. Python is one of the most testable languages that you can get into. It has hundreds of testing tools. We're going to talk about the very most basic ones here today. So for people who have never done Python testing, this is the place to be. If you've done Python testing before, there are 5 other talks going on while this one is going on. Right, so the concept here, why you want to test, is a basic premise that untested code is broken code. Everybody thinks they're the greatest programmer in the world, and that everything they write runs perfectly the first time, and you might write some code occasionally that runs perfectly the first time as it seems to you, and there's probably bugs in it that you don't even know about. So this idea of untested code is broken code came to me from a fellow who came and gave a 4-day Zope 3 boot camp to Tri-Z-Pug. He wrote the book on Zope 3 for Springer. His name is Philip von Weiershausen, and I don't know if he actually originated this quote or not, but when I searched for this quote on the web, the first at least 100 instances of it come up with his name on it. So I'm going to take it that he's the originator of this expression that untested code is broken code. Well, beyond just the fact that if you don't test your code, you know it's going to be broken, tests help you design good code. By making tests, you sort of get a feel for what your code is going to look like. You have to know what your code is going to look like in order to test it. Okay, we're going to stop for a minute for a microphone exchange. Oh, Carl, you're a gentleman and a scholar. Okay.
You're probably going to take your glasses off and just put it over your ear.
All righty. That.
Beautiful.
Okay, I'm going to back on. I'm blind without them.
Good, okay.
Okay. then we can take that one off, right?
Yep.
I can't see it, so do that for me.
Okay.
Thank you very much, Carl. And Carl is the pioneer who finally made PyCon video work. And we very much appreciate all your work in the Python community, because now PyCon videos look great. All right. Yes. So if I can't laugh at him, he can't. Next of all, testing is going to help you find your bugs, because even though you think your code is working, I can guarantee you that there are bugs in your code that you don't know about because you haven't tested all the corner cases yet. And what testing does is helps you find these things, helps you investigate your code with a little bit more granularity. And finally, many people will be surprised to find out that testing helps you document your code. In fact, some of the best documentation you can provide for code is providing tests, because it gives you a visual example of how your code is actually used in real practice. And let's start off with the most basic concept in Python testing. It's called the assert statement. And assert statements use a Python keyword. There's not very many keywords in Python, so you know that assertion and testing must be pretty important to Python, because it wastes an entire keyword on it, the concept. It's the assert keyword, all lowercase, A-S-S-E-R-T. And what assert statements are used for is to raise a particular type of exception called an assertion error. And whether these assertion errors are raised or not by an assert statement is controlled by a test expression, a Python expression that can be evaluated for Boolean equivalence. And most of the Python expression can be evaluated for Boolean equivalence by the bool built-in type. So let's take a look at an assert statement. It has two parts. It has the keyword. We're here at the Python prompt here. So if you're at a Python prompt, you can follow along with this. The 3 greater than signs Python prompt. The assert keyword starts an assert statement, and it's followed by an expression. In this case, it's an expression that has a Boolean value of true. 1 is equivalent to 1. That's sort of basic right there. So you have the assert keyword followed by an expression. That's the same, almost the same, as evaluating that expression in an if conditional, inverting the truth value of the expression with the not keyword. And if that conditional is true, in other words, if the expression is false, then you want to raise an assertion error. And if we have nothing else except an assert keyword and expression, then the assert error is raised without a message in the instantiation of the assertion error. So let's just take a look at an example of that in action. If we actually execute assert 1 equivalent to 1, nothing happens. It has no value. It's actually a statement. It's not an expression, so it doesn't evaluate to any Python value, but also didn't do anything. It just kind of acted like the pass statement at that point, if the expression in the assert statement is true. However, if we execute an assert statement in which the expression is false, in the case of 1 is equivalent to 2, we know that's false, then the assertion error is raised. We have handled this exception, and so that results in a traceback object. If we were running this in a program, it would halt the program. And the traceback tells us where in our program the assertion error occurred. So we can also provide a second optional expression to the assert statement that provides a message for the assertion error. Our first example did not provide any message, and this helps you distinguish one assertion from another in your code if you have many assert statements. Certainly the tracebacks tell you the line number and the module they occurred in, but you can provide yourself a better mnemonic than that. Line numbers change, module names change. You can provide exact names for your assertion errors by providing them as a message in your assert statements. Let's take a look at how that looks. A second expression there. We have the assert keyword, and then we have an expression that's evaluated for its Boolean value. And then that's followed by a second expression that will be used to instantiate the assertion error. That's usually the argument to establishing or instantiating an exception is the message used by the exception. In this case, we're going to say it's the string reality check. So that would be the same if we have an assert statement with 2 expressions in it. That's almost the same as evaluating that first expression. If it's false, raising the assertion error with the second expression as the message for the assertion error. In practice, it looks like this. So let's assert that 1 is equivalent to 2, which is almost certainly false. So that should raise the assertion error. Let's provide a message for the assertion error, in this case the string reality check. And we see when the assertion error is raised, and we see the visibility of that in the traceback object, we see that reality check is now the message. So we can label these assert statements by providing them the assert statements with the second expression. So what you really want to do in real life is sprinkle these assert statements throughout your code so that you can check that your code is running as expected. Those expressions that are being evaluated for truth or falsehood there should say something about the state of your program at any particular point. You think at this particular point in time, some identifier is going to be bound to a value. You can test that, and if it's true, then the assertion error will simply pass without effect. If not, it will halt your program and give you a message. So you can kind of think of assert statements as Python's version of a reality check. The thing is the reality check is for what you expect the code to be doing. So you get to decide what reality is in an assertion statement. All right. So any questions so far? For the most part here, I want to hold questions to the end, but I want to make sure everybody's keeping up here. So am I going at about the right pace for most people here in the room? Am I going too fast for anybody? Going way too slow for anybody? Wouldn't object to that. Okay. So let's assume that we have a Python script, and it's called BigBiz. And BigBiz is going to simulate a business model for our business. It's going to try to tell us what our profit is, and it's going to try to project what our profit will be in the future. And it's going to have a couple of functions in it. One's going to be called bottom line, where we can give some sort of date time object or some other form of timestamp. And it's going to tell us at that time what the profit is, and that'll be used mostly to find out what the profit is today. And we have another function maybe called growth, and we would give it a date time object that represents some instant in the future, and that would tell us what our profits are going to look like in the future. And so we can test this code by putting assert statements into it and asking these assert statements to tell us whether what we expect the code to be doing is what the code is actually doing. So we might want to test whether when we call the bottom line function to get today's profit, if the profit is 0. And if not, our business model wants to assert that that's just unacceptable, that we're showing profit right now. Next of all, we're going to have a function called growth. And when we call it with a future state, it should tell us what the profit is going to be in the future. And our business model, in our own mind, what we think reality should conform to is that profit in the future should exceed what profit looks like today. And if that's not the case, well, someone is going to get fired. And so this is what our BigBiz program is going to look like. And assertions usually generate some unhandled exception, and that will normally cause your program to halt. So anytime when we're executing this code right here, the first exception, the first assertion that is shown to be false is going to stop this BigBiz program. All right, so furthermore in BigBiz, we need to implement the bottom line and the growth function. And it's not really important to the person testing the code how these things are implemented. They're just going to simply test whether we think that these functions are doing what we expect them to do. But let's go ahead and let's implement the bottom line function in BigBiz. And that's part of that code package that you downloaded as well. And it is going to, by some method, determine what today's profit is. Notice that we provided a timestamp argument for it, and we completely disregarded it within the function, because we're just going to say that no matter what date that we give bottom line, we're going to say that the profit on that day is negative $1 million, or 1 million rupees, or whatever currency you're going to have. Python is not really specifying that here. So it's just going to return negative 1 million. In that case, we should be able to run BigBiz. And it's going to come to that very first assertion statement that tests. When I call the bottom line function and I take its return value and I bind it to profit, and the identifier profit, I'm going to test now with the assert statement the value bound to profit. And if it is not greater than 0, then I had better raise an assertion error and say that's unacceptable. And that's exactly what occurs when we run this script, because it's going to get back a profit of negative 1 million, which is not greater than 0. And so an assertion error is raised with the unacceptable message. So we can also use a feature in Python at this point if we're mystified as to why that's happening. Python provides a command line switch called -i. When you use that, Python runs the script and either completely finishes running it or it comes to some exception. Whenever it stops the program, instead of Python returning control back to your operating system, it leaves Python at an interactive Python prompt, and you have access to the main namespace of your script. So if we were to do that with a program with one of these, some of these assertion statements in it, and we come to an assertion that is false, we wind up at a Python prompt, and we can check out, well, why was it then that profit wasn't greater than 0? Oh, it's because my bottom line function is returning negative 1 million. I might want to take a look at bottom line and find out why it's returning that, because not always are the same person writing the code for it and writing the testing software for it. So the person writing the test might be something entirely new that the developer for bottom line knew nothing about. Well, of course, we were purposely developing a bad business model in order to demonstrate these assert statements. So you can also use that -i switch to get back to the Python prompt and then run the Python debugger. If you need to understand more than just the fact that bottom line was returning negative 1 million, you can use a Python debugger maybe to step through bottom line or to go back through bottom line and figure out what was going wrong. And so if you use Python and start with the -i switch to run BigBiz and you get the assertion error, you're dumped out there at the Python interpreter prompt, and you can import the Python debugger, and then it has a post-mortem function within it, so that you can say pdb.pm and then call that, and you'll be dumped into the Python debugger's post-mortem debugger that shows you where the error occurred again, and also allows you to inspect not only the variables in the main space of the function, but you can go up and down the stack frame if you have already nested calls and local variables of identifiers of any particular Python functions you have to be executing when the assertion error occurred. Alrighty, so assertions, it turns out, can be turned off by optimizing Python with the -O command line switch. Now, I say optimize because we say that -O stands for optimize, but actually optimizing Python is just sort of a misnomer in that when we use -O, what is actually happening is we're turning off the effect of the assert statements. It's not actually making Python run faster. There's nothing you can really do to Python at this point to make it run faster. We haven't crippled Python. We're not making it run slow on purpose or anything like that. But what you can do with the optimization switch is turn off assertions entirely so they're not even evaluated. Because sometimes in assertion statements we have expressions within them that are very expensive possibly to run. They might take a long time, and you can just skip that step entirely with the -O switch. Also, there's another way to invoke -O that kind of turns on twice, and all it does is remove doc strings from your code in the compiled code and makes your compiled code a little bit smaller. Doesn't run any faster, just makes it smaller. All right, so let's take a look at that. Let's go to our operating system prompt and jump into Python using the -O switch, and then run an assert statement where the expression is false, and we would normally expect this to raise an assertion error, but because we're running Python as optimized, the assert statement has no effect whatsoever. It's just like using the pass statement. So if you sprinkle your code liberally with these assertion statements, and you have gotten your code to the point where it passes all the assert statements and is no longer halting the flow of your Python program with some sort of assertion error telling you something's wrong, then you might be able to put that code in production with the -O switch and not worry about assertion errors ever halting your program again while that's running. And so we can do that with the Big Biz program. And even though we have 2 assert statements in there that we know should cause things to fail, even if we fix bottom line to return a positive profit, we still have to deal with the fact that growth here in this case is returning -2 million, which is an even bigger loss than today's profit of -1 million. And so the assert statements there have no effect with using the -O switch. With that, I would like to say it's kind of a fine line as to whether assert statements are testing or debugging, really. It's kind of doing both. You're sticking, it's kind of almost like using print statements in your code. Like the very first basic thing people do when they're trying to debug their code is they put print statements all over and see, are these variables what I think they are? So there's a fine line about whether that's debugging or testing, because people normally write their code and they don't put those print statements in there until there's something wrong. The idea to put things into your code before you know something's wrong so you can figure out if there is something wrong that you don't know about. So there's a fine line there between testing and debugging. The advantage of these assert statements are that, 1, that you can label them, and 2, that you can turn them off with a command line switch. And 3 is that even though hardly anybody uses assert statements to debug their code directly anymore, which is absolutely putting assert statements through their code, the concept of assertion itself is very fundamental to everything Python does for supporting testing beyond assert statements. All the test modules we have to do in some way use this concept of assertion. I'm going to make a statement about the way I think the program should be running at a particular point, and if that is not true, then I'm considering this a test case that has failed. So in Python, a test is an assertion of an expected result. It's your test of what reality is. Is my program conforming to reality? All right, any questions right here before we move along? Because we're going to jump into the next concept. Assertion as a concept is fairly simple, so we're not going to spend a lot of time on it. We're going to spend time on how that concept is applied in Python. So unit test is one of the batteries included modules in Python. Python comes with over 400 built-in modules at this point, and unit test is one of them, and it's the most fundamental testing module within Python, so we're going to learn about that. One of the things that unit test helps you do is separate your test code from the code under test. When we're using the assert statements, we have those assert statements sprinkled all throughout our code, and so we're maintaining both code and tests in the same file, kind of all mixed up together. Well, unit test helps you separate all that stuff out. You can have code that doesn't seem to have any tests. You can have tests completely somewhere else, and 2 different people can maintain them at the same time. Unit test helps you write tests before you write code. Now, that might seem a little bit backwards. Don't I normally write code, and then I try to test the code and see if it works? Well, Python supports the concept of writing tests before you write code. So you write tests, and then you simply write code to make the test pass. And when all the tests pass, you're finished writing code, because your code works, and it does what it's supposed to. It does what it's expected to do. Use tests to express what you think the code should do. Next of all, unit tests help you organize and discover all the tests in your code. If you're going to have code and tests in different places, you might need to discover where the tests are in order to be able to run them, in order to be able to get them to correspond to the code that you've written. And so unit tests provide you with tools to search your code and tell you where all the tests are in your code. And then finally, unit tests provides hooks that sort of stick their claws into all kinds of other Python tools that help you integrate your code into your normal production of Python code, possibly installing your code or publishing your code or documenting your code. Unit test gives you tools to help you do this, and we'll look at these here in this talk. Well, first of all, you want to be at Python prompt, so you import the unit test module, and if you use the dir built-in function to look at the unit test module attributes, you see that there are quite a number of attributes of this function, of this module, and we're going to try to simplify looking at these attributes for you by looking at the most important ones. The most important ones are listed first, and there are a number of classes that the unit test module provides for you, classes that we can use, specifically classes that we would like to subclass and write our own tests. So unit test dot capital T test capital C case. Unit test test case is a class, and you do not instantiate this class directly yourself. You write test cases where you write your own classes that subclass from test case. And then you add methods to your subclass of test case. These methods will have names that will all start with the string test, T-S-T, and you add these methods to your subclass, and then the unit test module will be able to actually automatically detect and use these methods to run tests on your code. That's the overall concept. We're going to look at some code for that in just a second. So each of these test methods that you supply in your subclass will execute some other method that the test case class provides, and all these methods start with the name assert, the string assert, A-S-S-E-R-T. So you provide methods that start with the string T-S-T, test something else, and then within those methods that you write, test case provides you with methods that you can call inside your test methods that say assert something else, assert something else entirely. So you subclass test case is provided to you, you provide methods, and in return again, test case provides you with methods to call within your test methods. So test case, when you write your subclass of it and you instantiate that, this provides what's known as a test fixture in testing parlance. Python did not come up with this way of doing things. The unit test module has like a long history to it. Before it was in the Python standard library, it had a name of PyUnit, and PyUnit itself is a port of a Java program known as JUnit, and JUnit itself is a port of a testing program for the Smalltalk language. Both the program for the Smalltalk language and JUnit were written by the same person. A lot of people came to Python from that background. They had a big testing background. They wanted to implement testing within Python, and they had this big background in testing already. They didn't try to reinvent the wheel. They used industry standard best practices for implementing how testing is done in Python, and so none of this was just like made up. So if it seems strange, the way that testing is testing is structured in Python, I would not disagree with you entirely, but it's the way testing has been done for about 30 years in the IT industry. And so rather than reinvent that wheel, Python decided to adopt the known best practices of the time. So this idea of a text fixture, you have a test case subclass that makes a lot of test methods that you write, that in turn use a lot of assert methods. So the unit test module also provides you with means of running these text fixtures so that you don't have to do so much work. A lot of the work is already done for you. You know, what a test case should be, what the assert methods are, and how to run all this stuff is built into the unit test module. You just provide the specifics that apply it to your code under test. So let's go look at a typical, no, I wouldn't say typical, this is pretty atypical actually, but a very simple Python script we're going to call test under operator. It's in the code that I had you download, and you can follow right along with that by looking at the code and writing it yourself, but we're going to get it on the screen right here. Test under operator is actually not going to test some code that we wrote, but the code is already written. This is very common that you have to provide tests for software that someone else wrote and they didn't bother to provide tests for it. And so the operator module is also included with Python. And it has test cases already, but we're simply going to use it to show what good tests should look like in Python, or at least what tests can look like in Python. And so our test operator script starts off first with a doc string, telling us what we're going to do. We're going to demonstrate the unit test module, and then we're going to import the operator module because that's the code we're going to test. So we need to have that within our namespace, and we're also going to import the unit test module. So the code under test is being imported, and the code being used to do the testing is also imported. So as I told you, first thing we have to do is we have to make a subclass of test case. And we're doing that here. We're calling our subclass test operator, and this subclass is unit test.testcase. So that out of the box right there provides us with a lot of things that we don't even know all the methods that test case has within it to start with, but let me tell you, there's many, many of them, and so it's going to save us a lot of coding right there that we're using this subclass. And as all good classes should, it starts off with the doc string. Test the operator module is what this test operator class is going to do. So within the test operator class, we're going to provide methods. And our first method is we're going to test the add function of the operator module. What the operator module does is it provides you with a lot of functions that simply implement as functions what Python operators already do. So the add function of the operator module will simply take two arguments and add them together and return that result. The same thing as if you use the plus operator. The operator module is there simply so that you can do functional programming with Python operators. You can pass them as arguments to other functions, and you can return them as results from functions. So that you don't have to deal with just expressions. You can also use functions in a functional manner, functional programming paradigm. Does the lights have to be turned off for this presentation here, or are they off by oh, okay. Is it totally necessary to have them off? I don't even know. Yeah, I thought I might not even be showing up on this tape here. So, plus I would like to see you guys too. You're a beautiful audience here today. All right, so while we're getting that turned on, let's take a look. So the methods that you supply in your test Okay, it's coming up red light. The battery says red light instead of green. Well, it was green now, it turned red. So they've actually dead batteries. That's awesome.
No, I try not to kid.
9 volts.
Carl, no one's going to ever equal your level of excellence, so just that's what it's going to be. Okay, so you can look at all the attributes in unittest.testCase and filter them for the ones that start with the string assert, and you'll see that there are many, many of these assert methods built into testCase. And if you find one of them, you can use Python's built-in help to take a look at what it does. Here's one called assert dict contain subset. You have to see if one dictionary is a subset of another dictionary. Lots of convenience methods. Okay, so we're going to make an ng2 instance of our test operator.py script. Next generation 2, the second generation, is actually the third generation of the test operator script. And it is going to, just like before, have a doc string at the top of the module like all good modules should, and it's going to import the thing to test and import the thing doing the testing. And then instead of a test operator class, we're going to factor out all the tests that have to do with the add function of the operator module into one class. So we're going to call it the test add class, and it's a subclass of unit test case. Pardon us while we change batteries. That is definitely a metaphor, isn't it, these days?
What the heck? It worked next door.
This is a power-hungry.
Maybe if we reboot it.
One bar. Guys, we got a little bit, few minutes past 5:50. I thought so. We got a lot of room. We got a lot of options. But I like to eat too, so we're not going to miss dinner. All right. Oh, I don't want to miss lightning talks. Good Lord, no. Okay. Oh, that's where all the cool stuff is, actually. So within our new test add subclass of test case, we're going to provide a test add int method to see if the add function of the operator module adds 2 integers correctly. We're also going to test it to see if supplying an integer as string results in a type error exception. So there's 2 tests there in test add class. We're also going to make a test subclass. So now we have more than one test case subclass in our test operator script. We have many of them. And Python will discover them all, instantiate them all, load them all, run them all, report all the results together. And so the test subclass is going to have a method to test if we can subtract 2 integers and if we can subtract a string from an integer, which should result in a type error exception. And a test mul subclass of test case is going to test if we can multiply 2 integers and test if we can multiply an integer times a string, which we can actually do. That does not result in a type error. We should be able to multiply the integer 2 by the string whose value is 2 and get a string whose value is 2. Huh. All right, so then at the end of this one, instead of calling unittest.main, I'm going to demonstrate how we can take all these different test case subclasses. We have test add, test sub, and test mul, and we're going to make what's known as a test suite, where we combine a bunch of test case subclasses. The way we do that is unit test provides us with a class called test suite that we can instantiate, and that will create for us an empty test suite, and we bind that to an identifier here we're just going to call string suite. Okay, so all of our test case subclasses we defined so far test both adding or multiplying or subtracting integers and integers with strings. I want to make a test suite that only has where we're testing integers and strings against operator functions. And so I can go to my test add subclass and instantiate that. Notice we've never instantiated our own test case subclass before. We're going to do it today. We're going to instantiate test.add, and we supply it with the string name of one of the test methods in it. And it will make a test case that only has that test method in it. And we can apply that as an argument to the test suite's instances add test method, and we'll add it to the empty string suite test suite. So now we have one method in there. We're going to add another method in there, the test sub string method from our test subclass. And we're also going to add the test mul string method from our test mul subclass. So we've added 3 methods to a test suite. We've selected which methods go into our test suite. Okay, so there's now 3 subclasses of test case in our test operator ng2 script, plus a test suite that we have added 3 methods to. And then down at the bottom, unit test.main, we instantiate that. And what is that now going to do? Don't know exactly what it's going to do yet. We're going to demonstrate this. The objects you have bound and the test operator ng2's namespace are 3 classes and a test suite instance. That's what we have. What is that going to do if we run it as a script? Well, if we run it as a script, then the unit test.main class is going to look through and find all the test case subclasses, all 3 of them. Each of them have 2 methods. It's going to run all 6. It's going to run all 6 of those methods from the three subclasses of test case. However, if we simply use unit test as a script and tell it what the particular test suite is that we want to run, that can be imported. From test under operator ng2, we can import things from that namespace, including that string suite instance that we created in test operator ng2. And that way we can run only 3 of those methods. We select what methods we want to run from what test case subclasses, and we make a test suite out of them. So test suite is testing nomenclature that Python did not invent. That came to Python from a long tradition of testing in the IT industry. In addition, we can use that -v switch for unit test and say, okay, I want you to identify for me what the particular test methods are that are in that test suite, and we'll show you the name of the test methods, which test case subclass they came from, and as well print out their doc strings, as well as only run those 3 tests in the test suite. All right, any questions here about test suite? The test suite, the test suite has an add test method that allows us to add particular tests from test cases, and we can make instances of those test cases by instantiating the subclass of test case and specifying as a string the name of the test method we want. There's other ways of doing this. This is the most basic way. There's ways we can automatically discover those things from test case subclasses. All right, no questions? Then let's move along here. Don't have too much time left. Let's look at how we can organize some tests. We're going to make a test package for a new package that we're going to create called PyCamp. Okay, so I'm in my PyOhio virtual environment. And within my PyOhio virtual environment, I know I'm there because I have a bin Python in there. And I have a PyCamp directory that I know is a Python package because the very first thing in the directory is an under.py module. That makes it a package. Okay, within my package, I have a setup.py that most packages are going to have. That's what enables you to install the package in your site packages directory and simply import them no matter where you start Python from. Within that package, we're also going to have 2 useful modules, one called Fibonacci.py that deals with Fibonacci numbers, and another one called Triangle.py that deals with triangular numbers. And then also in our PyCamp package, we're going to have a sub-package called test. And I know it's a sub-package because the very first thing in the directory is another under.py script. And within that particular test sub-package, I'm going to have 2 other scripts. One is called test under Fibonacci.py, the other is called test under triangular.py. And one of the things that unit test helps you do is not only separate your test code from the code being tested, but helps you put it in another place that can be easily discovered by things like setup.pys. All right, let's take a look at how this looks. We have written Fibonacci. It's not important what the code in Fibonacci.py is because we want to be able to test code where we're not even aware of how the code works. We just know how the code should work, how we should be able to import it, what it should do when we import it, and use the attributes within it. So I'm just going to say this is what Fibonacci.py should do. You should be able to run it from the command line and supply it with an argument, in this case, some number, and it's going to print all the Fibonacci numbers less than that number greater than 0. Fibonacci numbers are a sequence where each number in the sequence is the sum of the 2 numbers before it. It's very common in nature, and that's why mathematicians study it. So 1 plus 2 is 3, and 2 plus 3 is 5, and so on in that sequence. Also, if we're in Python, from the Fibonacci module, we should be able to import a function called fib and call it with an argument that's a number and get back a list of that same sequence. All the Fibonacci numbers less than the argument and greater than 0 in order. Okay, so anyone not understand what the Fibonacci script does, or importing the Fibonacci module and using its fib function does? It's pretty self-explanatory. That's sort of the API for the code right there, visually. Similarly, the triangular.py script, when we run it, supply it with a command line argument of a number, prints out all the triangular numbers that are less than the argument and greater than 0. And triangular numbers are the one where it's the sum of all the indexes in the sequence up to that point. So 1, and then 1 plus 2 is 3, and 1 plus 2 plus 3 is 6, and 1 plus 2 plus 3 plus 4 is 10, plus 5 is 15, plus 6 is 21, and so on and so on and so on. This is also very useful. Use a lot in mathematics. If you're familiar with something called Pascal's triangle, it's used there. It basically describes if you have a triangle, like a billiards triangle, and you put balls in it, the number of rows of balls in there will index this sequence and tell you how many balls are in that triangle. So also, if we're within Python and we import the triangular module and use its try built-in function, we should be able to pass it a numeric argument and get back a list of all those triangular numbers less than that argument and greater than 0 in order. So that's how Fibonacci.py and triangular.py are used. That's all we need to know about. We don't need to know what the code in them looks like. However, we do want to look in the test subpackage of PyCamp, where Fibonacci and triangular modules are, because that's where we're going to test those modules. Within there, we have scripts called test under Fibonacci and test under triangular. And so test under Fibonacci.py starts with a dot string and tells us it provides test for the Fibonacci module. It's also going to import the thing being tested from PyCamp, import Fibonacci. It's also going to import the code that we use to do the testing, which is the unit test module. And then it's going to make a test case subclass we're going to call test Fibonacci, and it of course has a dot string as well. Now, test cases also allow you to supply methods that are overridden in test case. In other words, test case provides a number of different methods that you can override. You can override what assert equals does. You can override what assert not equal does. But more importantly, it provides you with a couple of methods called setup and teardown, and those you typically do override. You don't normally override the assert methods, but you override setup and teardown. And setup is a method called when your test case runs. It's called before every test method in the test case. Over and over again, every time that test method is run, test setup is run first, and you can set up a text fixture with that. And after your test case runs, teardown is called. And so you can supply things that set up conditions for your test method to run and then get rid of them after you finish running. Like if you have some open file connections or open network connections, you might want to close them. So to reiterate what a text fixture is, your test case subclass, along with all the test methods that you supply yourself and all the test case methods that you override, like setup and teardown, are possibly all bundled up into a test suite with methods and overrides from other test case subclasses. All collectively, they are also known as the text fixture in testing parlance. So let's go back and let's look at that test Fibonacci subclass we're making again. It has a setup method, and the setup method, we're going to decorate our test case subclass instance with an attribute called less than 100, and it's simply a list of those Fibonacci numbers less than 100 and greater than 0. Gives us something to assert something equal to later on in our test. Okay, so once we have this thing set up, this decorate on self, we can reuse it in our other test methods because they all also have access to self. So in test fib 100, we have a dot string, of course, for that test method. Then we're going to assert that calling the fib function of the Fibonacci module with the argument 100 is going to result in something equivalent to the less than 100 attribute of our test add instance. Okay, and that should be true. We've already kind of seen that's true. And we're also going to have another test that's kind of gratuitous. If we call the fib function with the argument of 10, we want to see that we have all the Fibonacci numbers in a list returned to us that are less than 10, and that happens to be the first 5 elements of less than 100. So we can simply slice that, and then setup has created that sequence for us that's there available for us to use to slice up and compare as we need to. And then finally, we're going to use the main class of unit tests to run the test Fibonacci instance. And similarly, test triangular does the same sort of thing. It imports the triangular module we need to test, imports unit tests, sets up a test triangular subclass of test case that has a dot string, has a setup method that we set up our test list in, and has a test method for testing try called with the argument of 100, and one for calling try with an argument of 10. Alrighty, so it also has a main instance in it. So we can use, now at our command line, if we're at the PyOhio directory, we can call the unit test script as a module and use that discover command and say, I want you to start searching in the PyCamp package. I don't want you to search test operator and test operator ng and test operator ng2 or anything else that might be there. I want you to start looking in the PyCamp package, and when you find tests in there, I want you to run them as if you were importing from the current directory, because the current directory is actually where we can import from the PyCamp package. Okay, so if we do that, we see 4 dots, all the tests ran correctly. So there's an example of using the -s and the -et to specify where to start searching and where to start importing from. Okay, now why would we need to do this? Why would we want to separate all those tests into a separate directory with separate test scripts for each of the 2 modules that are useful in the PyCamp package? Well, that's because Python allows us to have a setup.py script in our package that if we import something called setup tools into, that's an add-on package for Python. We used to do that with a built-in module called disutils. The modern way of doing it is to import setup tools, and you can either get that the old way from the setup tools that Philip Eby wrote, or the new hotness is to get it from a package called distribute that I'm sure you've heard about. Who's heard of distribute? It's like all over the Python blogs. You use easy installer pip to install distribute, and that gives you a module called setup tools that you can import a function from, called setup, and having a setup.py with a setup function in it that you simply call. Setup tools provide you the function. You call it, and you provide it with keyword arguments. One of them is name. You can tell what the name of the package is and what the version is with the version keyword. And you can use the find packages function that setup tools provide to search your packages for package modules to add to the overall package being created by Setup Tools. You can tell it who the author is of the package. You can give an author email. There's all kinds of different keywords. Not all of them are required. Some of them are pretty standard. Those are pretty standard ones. You can provide it with a description. If this looks very similar to the descriptions you see Python packages on the Python package index, there's a reason why. They come here from the setup.py module and the setup function. You can specify what the license of your package is, what the keywords are for searching for it in the Python package index, the URL to where the website is for it. And notice this very last one, test under suite. In test under suite, you specify to the setup function where the test cases are for this package. They can be imported from the pycamp.test subpackage. So specify that in the setup.py, and what Python then allows you to do, and Setup Tools allows you to do, this is where unit test has hooks into other Python tools. And Setup Tools is one of the most important tools in Python. It allows you to create and distribute Python packages. It takes many different arguments, and one of them is test. And when we call setup.py with test command, it will let me test suite attribute that we created there with the test under suite keyword argument to the setup function, and it will run all those tests. And so we'll say it's running tests. It'll have a whole lot of output because it's not only running the test, but it's like building the entire package, it's building a temporary copy of it, running all the tests, and then tearing down the package that it created, and tells you how many tests it ran and what your success was. And so let's just demonstrate all that output right here. Python. Let's look in the PyCamp package and run the setup.py script and give it the test command. You see it building a package there, then it ran all the tests in verbose mode and reported the result. So this is one reason you're going to segregate all those tests into particular modules that start with test in a test subdirectory. That's pretty standard. You do that so that you can use that particular subpackage in a setup.py script. The reason you would put that to a setup.py script is not only so that you can run all the tests, that makes it very convenient to run the tests for one thing, but also when you install the package into Site Package, you can install all the tests and run them anytime and make sure the package is still running. And also, setup.py allows you to do the register command that creates all the paperwork that you need to upload your package onto the Python package index. And if you upload a package to the Python package index and it doesn't have tests, then you'll show up on Python package ranking websites. Your package will show up there with a very low score because it did not have tests. There are websites that go out and look at all the packages on the Python package index, see if they have tests, see if they have good test coverage, see if everything in the package is tested, and ranks your module against all the other Python package Python package index packages to tell how well you're doing against all the others. And in fact, if you're thinking of using a package, you want to go look at one of these websites or look at the package itself. Does it have tests? Are the tests comprehensive? Do they all pass? I might want to try using this module. So the unit test provides a nice separation of tests from code, and it provides such that one person can write the test and another person can write the code. You don't even need to know what the code, how it's implemented in order to write the test. Just need to know what the expected results are. Unit test provides this very fine-grained control over what tests to run. You can segregate things into suites and run only the tests that you want at a given time, and it conforms to industry standard testing practices. All right, any questions there about the unit test module before we move on? All right, we want to move on in just a little bit here because it can be difficult to keep your test and code in sync. You write a bunch of tests, and you write code to make the test pass. You've got a nice package that's all tested. You can upload it. Then later on, you go, I wish I'd added this other feature to the code. You go add that code to the package, but then you don't add test cases for it because they're in some other place. You just out of sight, out of mind, didn't think about it. Or you might have provided tests for it, but you haven't got any code element with it. It's kind of hard to keep in sync a little bit. Also, writing code to test code can be even more difficult than writing the code itself. It's very easy to make errors in the test code that you write, and sometimes it's sort of abstract about the search methods that you need to call to test your code. Also, what about in debugging and testing the test code itself? If you're going to make errors in it, you actually probably want to be able to test your test code. There's a never-ending loop right there checking any problem. And reading unit tests is actually a poor way to figure out how code works. Remember at the beginning of this talk we said that testing Python code should enable you to document how your code works in your test. Well, I think reading assert equal and assert dict contains subset sort of methods are a very poor way to document your code. It's like a lot more stuff to read through than actually reading the code itself. So obviously we haven't solved the whole pickle right here. So informally, so I get some extra time maybe? Okay, great. So informally, even without written tests, you probably already test your code. I mean, you write code, and then the next thing you're going to do is you're going to see if it works. And if you see if it works, is you go to your command line, you run it with Python, you import the code, you start trying to use it. You do this already, even though you might not write formal test cases. Informally, you probably test your code if you write some code. So you probably imported your code to the Python prompt and spec out works manually. You just don't have a way of repeating these tests that you do at the Python prompt in an automated manner. It'd be great if you can repeat this code, this type of test, because every time you need to make a test change in your code, you need to be able to run these tests again. If you have to do the manual testing all over again, that kind of gets repetitive, especially if you're making a lot of changes to your code. That's called regression testing. That means I can run the same test and they still pass even when I make changes to my code. You want to make sure the test cases continue to run. So what you need to do that is you need something called the .test module. Very, very interesting. So just as we had a test operator ng script, we're going to have a PyCamp ng package. It's also still going to have the Fibonacci.py and the triangle.py script in it. It is going to have a test subpackage. It's only going to have one script in the test subpackage called test under PyCamp.py. Okay, so that's what the structure of the PyCamp ng package looks like. All right. However, now we're going to get into the actual code of Fibonacci.py. We're going to look at that. The Fibonacci.py module has a doc string at the top. And in the doc string, I not only tell you what this module does, but I put some text in there that looks like a Python prompt. It says import Fibonacci. And if I do that at the command line, what normally should happen is the module imports and goes back to the Python prompt, right? That's normally what happens. If the module is not importable, I'll get some sort of traceback message. It tells me can't find this module, or that module doesn't exist, or that module has a syntax error in it, or something like that. So we put exactly what we would do in a Python prompt to test this module into our doc string. Then, if we look at the fib function within this script, we have another doc string, and this doc string tells us what the function does. It provides sort of an abstract example. It says if you call this with an argument n, you're going to get back a list of Fibonacci numbers greater than 0 and less than n, where n is an integer type. So that's a text description of what it does. But then, also within that doc string, see the doc string is closed there at the bottom with triple quotes. It's a multi-line doc string. We're going to draw something that looks like a Python prompt. And we're going to find some identifier, less than 100. And we're going to bind it to a list object with Fibonacci numbers less than 100 in it and greater than 0. And just like we could hit in the middle of that list definition, we could hit enter, and we get 3 dots back for the Python prompt. And we can continue making that list. We can put 3 dots right there in our doc string. And then when we're finished defining that list and hit enter, we should come back to a Python prompt 3 greater than signs. And we can call the fib function, supply with an argument, and we should be able to test whether the result of that fib function is equivalent to the less than 100 value. If that is, then Python should report that to us as capital T true. Should evaluate that expression. It's a Boolean expression, and should report back to us that it's true. And similarly, if we call it with the argument of 10, then we should get back the first 5 elements of less than 100 and be able to say, are these things equivalent? And Python should say true. So we draw out the very things that Python will do. In fact, we could go to a command line, we could enter these things and cut and paste them directly into our doc string. Okay, so if we do that, we should also be able to do it for triangular.py, where we have a doc string for the module, and we have a doc string for the function try. We have some text information, and we also have an example of using it from a Python prompt. So we just have 2 doc strings in there, one for the module, one for the function in the module. And we've put some things in there, things that look like they might be a test. Okay, so what we can do is we can go out to the command line prompt, the operating system, and invoke Python with -n and say, Python, instead of running the unit test module, run the doc test module as a script. And the doc test module doesn't try to import something. You tell it where the script is as a file. Okay, and what the doc test module does is it goes and inspects that file and sees if there are any doc strings in that file. And if so, it constructs doc tests out of all those doc strings in the file and tries to run the Python examples in them. It tries to execute all the commands that are Python prompts, and then when it does that execution, it gets some result back from that execution, and it compares that result to what you said the result should be. And if they're true, that's a passing test case. And if they're different, that's a failing test case. So it turns out that we can simply go do that, right here. Let's do that from a command line. If we execute that, we'll get some report back. First, it's going to say it's trying the test case that are in the modules doc string. It imported Fibonacci and expected to get back nothing. It should simply go right back to the Python prompt. And in fact, that's exactly what it did. So it reports to us, okay, that's a passing test. Then it will try to bind this list to the identifier less than 100. That doesn't result in any value. That's an assignment statement. It doesn't have a value. It binds a value to an identifier. It doesn't result in any particular value. And so it expects nothing. It gets back nothing. Okay, so then it can also try calling the fib function. It has, the doc test has access to the main namespace of the entire module, so you can simply call fib with an argument and see if it compares to the value of that identifier less than 100. And we expect Python to say that's true. It compares that to what we put in our doc string. They're the same, so the test case passes. The same for calling fib with an argument of 10. And then finally, it reports to us that 2 items passed all tests. What were those 2 items? They were the module and they were the fib function. So we provided doc test not only for the fib function, but for the entire module as well. And it tells us how many test cases were in each. In the function, in the module, we simply had a test case to import it. In the function, we had 3 test cases, 1 to set up an identifier, that's sort of like our setup, and then we had 2 test cases for equivalence and calling the fib function with different arguments. There's 3 tests, 4 tests passed and 2 items. 4 tests passed and 0 of them failed. All the test passes, we're back. So let's do that in real life. Python-m .test, run the .test module, and look in the PyCamp package. Is that PyCamp or PyCamp NG? What is NG? Yeah, NG. Okay. Oops. Get back to where we're going. Okay. PyCamp in NG. And Fibonacci, right? Don't believe, do we need that? I don't think, yes, we did for this one, yes, right. What do we get if we just run like that? We get nothing. That's what doc tests do. If you don't provide anything verbose, you just follow the test paths, it doesn't say anything. Test fails, it informs you of it. Here, all they pass, so we want to see some verbose outputs, so let's add -b. And it prints out all this stuff for each test case. Okay, so that looks a lot different than running unit tests, doesn't it? You don't have these dot business, and it prints out, what it's actually doing, what it expects, all this kind of crazy stuff. Alrighty. So I think we're officially supposed to end here, so anybody who wants to go to Lightning Talks can go run and do that. I'm just going to talk for a few more minutes about doc tests. We'll be wrapping up real soon. Anyway, we can do the same thing for triangular and get the same results. Let's go back here and let's change Fibonacci.py one more time. Let's say that in the if main is equivalent to main part of it, if we get an argument that says test, then we're going to import doc test. And here's another way that you can run doc tests is by using the doc test test mod function. And we'll say run all the doc tests in this module. Otherwise, we're simply going to call the module as a script and provide it to have it do something useful, which is take the command line argument and compute those Fibonacci numbers. So do the same thing for triangular.py. So now we should be able to call Fibonacci.py as a script and pass it the argument test. It runs all the doc tests. We supply it with a numeric argument. It will supply that to fib and print out something useful. So now we can use if name equivalent to main for both testing and doing something useful. The same thing for triangular.py. So what about setuptools.setup? That was geared for unit test discovery. Setup tools will go look for unit tests based on that test suite keyword argument we get to the setup function from setup tools. It doesn't do doc test discovery, it does unit test discovery. So what you really need is a way to turn doc tests into unit tests, and it just so happens that doc tests comes with a very useful class called doc test suite that searches a module for doc tests and converts them into a unit test.test suite instance. And now all you need is a way to communicate that test suite instance to your unit test discovery. So it turns out that the unit test module provides another way of discovering unit tests. If your module provides a function that looks like this, it's called load test, and it has 3 arguments. They can be called anything, but typically we call the parameters loader, test, and pattern, and it returns a test suite. So if your module provides this, what unit test is going to do is call that function when you do unit test discovery. It will pass a default test loader instance. It will also pass in an empty test suite that allows you to fill the test suite with your tests within the load test function and allows you to change the search pattern for any additional searches that you might do in your load test function. And then you can return a test suite full of doc tests that you have converted into unit tests. So let's take a look at test under PyCamp.py in the test subpackage. We import doc test. We import Fibonacci, and we import triangular. So the thing we need to do the testing, and 2 things that we want to test. We define a load test function, and unit test calls this and provides the arguments. It provides us with a loader. We're not going to change what the loader is, so we're just going to not disregard that. It's going to for a test case. So we can call doc suite built-in class and provide it with a module. It will discover all the doc tests in that module and convert them into unit tests. And then the test suite provided by unit test has an add test method that we can add to the test suite provided by unit test, all those doc tests that we turn into unit tests from the Fibonacci module. And we'll do the same thing for the triangular module. So that's pretty sweet. Allows us to put everything into one script. And then we're going to return that test suite instance that we modified, that we filled up. We got an empty test suite from unit test. We add a whole bunch of tests to it from doc test. And so there's where doc test allowed us to do the conversion. And here's where unit test allowed us to add those to the empty test suite. And we return that, and now we're going to use it in setup.py because now we have discovered a unit test that we can test suite that we can identify by searching the PyCamp ng.test. It will look for all the modules in there that start with test, which is like test under PyCamp.py. It finds the load test method in there that creates a test suite, which is then returned by all this and assigned, bound to the test suite keyword of setup function in setup.py. And so now when we call setup.py from Python and provide it with the test argument, it runs all the doc tests. Let's check that out. Python-n, what's it actually? No, PyCamp, G, setup.py, test, provides us with a lot of output. We can also install the module, and we can register it for upload to PyPy with that same setup.py. Hooks in the setup tool. So it's together, doc test suite function and the load test protocol from the unit test module enabled you to use the tools available for unit tests with doc tests. So that's a good thing. Unit tests and doc tests work together, and all the testing mechanisms in Python are pretty much built on top of unit tests. In fact, you can click on this image there in the presentation, or you can search for in Google Python testing tools taxonomy, and you'll come up to a page on python.org where there's a list of several hundred testing tools based on unit tests. So with these tools, we can do what's called test-driven development, and that's where you write tests for your code before you write code, and you write code to make your tests pass. This seems like a strange way to do development. You're not alone. However, it provides many rewards when you do it. First reward is when all your tests pass, you finish coding. You can define when your project is done. You can make an agreement with your boss. This is what we're going to have the code do. This is what we expect. I'm writing these tests, and when they pass, the project is done. We can say we're finished because we did what we agreed to. You can also develop your code incrementally. You can write one test. Can I import a module? I got it to pass. And so you can stop coding at any time. You can decide, I spent enough money now. I made these features, and I can stop spending money. So you can write a test and import the module. That works. So I want to stop now. I got some more money. I want it to do more. So I'm going to test if I can run this function. And does it pass? Yeah. I'm going to add another function. I write a test for it. I make it pass. I keep going, and I decide when to stop spending money. So if your code needs more features, then what you really need is more tests. You add more doc tests, and you make code which makes those tests pass. When you write those tests, you can see with doc tests, because you put things in there in a Python prompt, what the API for your code is, and you can make it documented in your doc test. And because Python has all kinds of documentation tools, doc tests, to write documentation, then your test cases, your doc tests, go directly into your documentation for Sphinx that gets uploaded to read the docs. And so writing tests can provide the documentation for your code. It might not provide all the documentation, but it can provide some pretty good documentation that you probably won't have to write as much. And so if you click on this page right here, you'll be taken to a page on the internet where we have what's called a Python cone called the Backward Monk. And I don't know if I want to take the time to read through that right now, but I would highly encourage you to go look at this, because tomorrow at 12:15 in this very room, Greg Malcolm is going to give a presentation about test-driven development. He's going to use these methods, and he's going to use Python cones to show you how to write doc tests and test cases and unit tests, write tests first, and then write code to make the test pass, so that you will be doing test-driven development. And so I'd like to say thank you. If you have any additional questions, you can mail them to me at pycamp@tryzpug.org. I'll be glad to answer them. And thank you for sticking around an extra 7 minutes, which I think is how much we burned up. Thanks.